Hello everyone and good evening. Welcome to the OneClass channel. My name is Fejiro and I'm an honors Bachelor of Science graduate currently working towards medical school. Today we're going over some commonly asked chemistry questions at both the high school and college levels. If you need some homework help or just some extra tutoring, please check out the links in the description below. With that being said, we're going to hop right into this session, starting with, well, actually even before that, just want to say Happy New Year's to all of you, for those that are watching. And yes, so let us start with the first few questions of the new year. So question 1 is asking us to draw the Lewis structure for a hydroxide. Okay, and they give us what the hydroxide is, but I do recommend that you memorize this. So hydroxides, you kind of get a hint based on the name because you see hydroxide. There's a hydrogen and an oxygen side of this, which is how you get the HO, but they write it as OH, and it's going to be minus. That's the charge it is. So please do memorize this because especially when you work with acids and bases, this does occur frequently. Okay, so now they're asking us for the Lewis structure. So first we have to actually figure out how many how many electrons each atom contributes. Okay, so for this we have oxygen, and oxygen is on the 16th column. Okay, another way you can do this as well is if you broke it down by its the electron configuration. If you wrote it in the shorthanded form for noble gases, you will see that oxygen is helium 2s2 2p4. Okay, and hydrogen, because it's literally the first element, it will just be 1s1. So because of this, we know that oxygen can give, based on the superscripts, in total 6 electrons, and based on the superscripts for hydrogen is going to be 1. Okay, so currently we have 7 electrons, but you notice right here it says OH minus. Because of that, you add an extra electron. Minus for electrons means that you're adding more of them since electrons have a negative charge. So in total we have 6 plus 1 plus an extra 1. So we need 8 electrons, okay? So we're going to just first draw the hydrogen and the oxygen next to each other. I just added a bond there because there needs to be at least one bond, signified by 2 electrons between them. Now, based on this, okay, hydrogen so far from here, you can see that it's currently sharing its only electron it can share. But oxygen is sharing 1 of its 6. So then I would fill out the rest based on how many oxygen still has left. So I would go 2, 3, 4, 5, 6. So that's oxygen right now, almost a complete octet. But you notice that you still have that 1 extra lingering electron. So there is how oxygen completes its octet. This will be the Lewis structure for hydroxide. I'm going to actually go out the way to even find out its formal charge. Okay, let's start with the hydrogen, just see where the charge is. So hydrogen, its valence electrons based on the periodic table being on the first column, it'd be 1, and subtracting how many electrons it has by itself, which is 0, and how many it's sharing. It's sharing 2 electrons, but because it's being shared, you have to divide by 2. So that would be, it'll be plus here. So in total, it would be 1 minus 1. So 0 checks out. Hydrogen currently has a neutral formal charge. Now for oxygen, this electrons is 6. Okay, it has 6 electrons by itself, and just like the hydrogen is only sharing 2, but 6 plus 1 is 7, and you notice that's where your negative charge is. So theoretically, your formal charge should add up to the charge of the ion. In this case, it's 1 negative, which is what this adds up to. So this right here is our final answer, is going to be the Lewis structure for hydroxide, and also you'd want to add that it's going to have that formal charge there. That negative near the oxygen, okay? So don't mistake that dash for another electron. That's just me indicating its charge. All right, so let's see how we did here. So as they did, they drew out the oxygen and hydrogen, added the bond between them, then they filled out the rest. The bond signifies the 2 electrons, and then they filled out the oxygens and added the extra electron to complete the octet on the oxygen. And with that, this is going to be the Lewis structure for hydroxide. All right, so this is correct. Let's move on to the next question. This is going to be another Lewis structure question. It's asking us to draw Lewis structure of oxygen dichloride. I would assume that would be what it's called. And we have to then use the Lewis structure to identify whether it's nonpolar, whether the molecular geometry is linear, whether the central atom electron geometry is tetrahedral, the structure has 1 lone pair, or the structure is drawn with 20 valence electrons. So we're actually going to go in a different order. I know we have 1, 2, 3, 4, 5, but I can tell you right now 5 is going to be the first one we answer, because of the fact that in order to start with the Lewis structure, what I like to do is figure out how many electrons I'm working with in the first place. So oxygen dichloride, we have an oxygen and we have 2 chlorines. So we go to the periodic table. You can find out what the amount of valence electrons we're dealing with based on either where it's located on the periodic table, or when you deal with transition metals, you can also try to figure it out through the electron configuration. I just like showing the electron configuration so that people get comfortable with it. With that being said, the shorthanded version for oxygen would be helium, because that would be the noble gas, followed by 2s2, 2p4. And then for chlorine, we have neon, followed by 3s2, 3p5. Reason being because it's on the 17th column, and you should see that the superscripts here, the 2 and the 5, should add up to 7, which makes sense because that's typically the amount of valence electrons things have on the 17th column. The oxygen, you notice it's a 2 and a 4, which is 6, which also makes sense because that's the amount of valence electrons things in the 16th column have. So now for electrons, we have 1, 6, and 2, 7, so that's 14. In total, the amount of electrons we're working with then is indeed 20 electrons. I wouldn't even say valence, just 20 electrons, okay? So with that being said, the structure is drawn with 20 valence electrons. That's number 5 is correct, as far as we know, because considering we don't have any, this is not a ion, it has a net charge of like neutral 0. We only have the electrons given based on the valence electrons of each atom. Well, 5 is correct / true. Okay, so we solved that one because 6 plus 7 plus 7 is indeed 20. Now let's go ahead and actually draw the Lewis structure. Okay, so because oxygen is a unique one, we're actually going to put that one in the middle. We have O. We're going to add 1 bond to both sides, just assuming there's at least 1 bond. We have the chlorine and the second chlorine. Okay, so firstly, starting with the chlorine, we want to now fill out the rest, because technically speaking, chlorine is now sharing 1 of its 7 electrons. So the way I like to count is I go 2, 3, 4, 5, 6, 7. Same with the chlorine on the other end. 2, 3, 4, 5, 6, 7. All right, and now oxygen is sharing 2, because it has chlorine on each side, 2 of its 6 electrons. So what I do is 3, 4, 5, 6. So coincidentally, this is a Lewis structure for oxygen dichloride, and this is completely balanced already. In fact, if you were to count the electrons, you will see that we're actually still working with 20, because each chlorine would have 8 around it. So that's 16, and then plus a 2 here and 2 there. So that's 16 plus 4 in total. is indeed 20. So now that we have that, let's now figure out what we're working with in terms of its polarity. Now, in order to answer that question, we actually need to find its electron geometry. So that would be 3. But before I even go there, I noticed that what question 4 was asking. Okay? Question 4 is asking the structure has one lone pair. So as you can see here, when they refer to lone pair, they're typically talking from the perspective of the central atom. I count 1, 2 lone pairs because a pair is 2. So with that being said, 4 is false. So now we've answered 2 of our questions so far because there's 2 lone pairs instead of 1. Now, to find the electron geometry, what we do there is, in a sense, we need to find its hybridization, and that is based on the things it's currently attached to. And when I say things, I mean either electron pairs or bonds. No matter the type of bond, the bond counts as 1, and the electron pair counts as 1. So if we counted, we had, well, not have, we have 1, 2, 3, 4 things attached to it. So it's hybridized to the 4th level. Well, there's 4 things attached to it, and because of that, the way it works for it is that we have sp3. The reason why, because in the orbital for s, there's only 1 orbital, and each orbital can fit 2 electrons. And for p, there's 6 orbitals. There's 3 orbitals, and each orbital there can fit 2 electrons, meaning 6 in total. So that's how we have sp3, because if you count it, this should equate 8 electrons that can fit there. And that is indeed what we have in regards to this. We have 1 s and 3 p's. That would be how you write that hybridization. So it's sp3 hybridized, okay? And when something is sp3 hybridized, the electron geometry is indeed tetrahedral. So with that being said, 3 is true. Okay? That is correct because it's sp3 hybridized, the electron geometry is indeed where is it? There we go. The electron geometry is indeed tetrahedral, and that's how we can actually get that. So now it's asking us for, we can just go up. The molecular geometry is linear. So here for molecular geometry, now we actually care whether the thing it's attached to is a lone pair or a bond. In this case, as we said in the electron geometry, we have 4 things attached. But as you can see, they're not all bonds and they're not all lone pairs. Instead, we have a 2-2 split. 2 bonds and 2 lone pairs. So when you have that, the name, the molecular geometry shape we get wouldn't be linear, but it would actually be kind of like this. And we call this shape bent. And that's actually what happens to the molecule water. Because H2O, it's the same thing, except hydrogen does not have lone pairs on its actual atom. But with that being said, then, that means 2 is false. Because it's not linear, it's bent. Now, the last question is asking is that the molecule is nonpolar. So, had it been linear, okay, the chlorines would be equally pulled on each side. It would make for a nonpolar molecule. But because it's bent, the actual lone pairs itself has its own type of pull it can exert on the molecule. So because of that, this is no longer an even distribution. Okay, the forces don't cancel out. You have one side here that's the chlorines and one side here that's the lone pairs. It's not an even distribution. The molecule is going to move either up and down based on which one is a stronger pull. Because of that, there is a directional pull of it, we can no longer say that the molecule is nonpolar, because nonpolar molecules are equally balanced in all directions, which this is not. So with that being said, 1 is false, okay? Because this molecule is indeed polar. All right, so that's how I would go through this question. As you can see, we kind of went from bottom up process because we had the 20 valence electrons. We saw how many lone pairs, we saw the hybridization, and then we found its molecular geometry, allowing us to then figure out its polarity. So with that being said, they do have the picture in terms of the Lewis structure. Based on that, they show that it's bent molecular geometry. Because of that, it's net dipole moment, and it is indeed polar. So as you can say, statements 3 and 5 are correct. As we see here, we only got 5 and 3. The rest of them were false. So yeah, this is correct. And now we can move on to the next question for today. What is the oxidation state of each element in K2Cr2O7? So for this one, unfortunately, it does require a bit of memorization, but if it does help, I'll try to break it down as much as possible. So right here, K2Cr2O7, that is potassium, I believe, permanganate. No, dichromate. Potassium dichromate. I don't even know where I got permanganate from, but this element is potassium dichromate, if I remember correctly, because I believe that's a dichromate ion. Now, with that being said, though, because of that, I like to now separate in terms of the different, I guess, ions of it, like just separating the metal and non-metal. So I have K plus and Cr2O7, 2 minus because there's 2 pluses in there. The reason why I'm doing it this way is just to briefly show you, because there is a proper way to handle this, but I want to briefly show you that specifically the potassium, when you are dealing with alkali metals, the oxidation state is typically +1. Reason being because they typically just get rid of an electron. That's it. So for example, potassium, in this case, as you can see here when I separate it, even though we have 2 potassiums, each of them just has a charge of +1, because the oxidation state, as I said, even in the answer here, considering it's an alkali metal, on the first column, it's just going to be +1. This allows us to now approach the dichromate part specifically, because there's also a rule that we also follow when it comes to oxygen, and that allows us to simply isolate for the chromate part and figure out the answer. So let's write out again. We have K2Cr2O7, right? Okay, so as we discovered, potassium is +1, and there's 2 of them, so that would be +2 above. Okay, now as I was saying, oxygen has specific rules in regards to its oxidation state. Oxygen, unless you're dealing with peroxide, which is H2O2, it kind of follows the same thing with the alkali metals, but instead for its own row, I believe column 16, where it just, most things there, well, it's not even most things, just specifically oxygen, likes to always be -2, okay? And you notice, right, potassium dichromate has a net of 0, so you want to make sure all your numbers at the top add up eventually to 0, okay? But yes, oxygen, -2, all right? It really loves to just take 2 electrons from its environment. The only exception, as I wrote here, is H2O2. I'll put that in red because this one doesn't apply here. It's just an exception, because here oxygen is just +1. I mean, not +1, -1. Very strange phenomenon, but in this case specifically, Oxygen is not -2, it's just -1. But that's only for this scenario here, which does not apply in this question. So like I was saying, oxygen is -2, okay? And because there's 7 of them, that in total is -14, okay? So now we have +2, -14. In total, we're right now -12 deep, and we want to make sure we can have a neutral molecule. So because of that, the chromate specifically has to be, in this case, +12. Because that's the only way all this at the top ends up being a neutral 0. And because there's 2 of them to get to +12, that means each of them has to be +6. So now they're asking, as the question says, the oxidation state of each element in potassium dichromate. We have potassium is going to be +1, chromium is +6, and oxygen is -2. At least that's what this would be, specifically to make sure that the element ends up with a net charge of 0. So as you can see here, oxygen is said to be -2, potassium +1, and then they filled it in kind of like how we did, and then end up with +6 as the leftover. So the oxidation number of chromium was indeed +6, and this is correct. So let's move on now to question number 4. I thought I removed this question. What is so for this, they're trying to find the bond in the peroxide ion. But for this one, because here, we're actually going to skip this question for now. So let's just move on from it. Trying to figure out how to skip this. No worries. We'll get back to that. Okay. Now, we have this question here. What is the conversion from quartz to pints? Okay. So with that being said, this one is relatively straightforward. You want to make sure we're converting from quartz to pints, and that's what they state. We start with quartz, we end with pints. So we're going to have X quartz times a certain relationship is equal to something pints, a certain amount of pints as well. So we want quartz to be in the denominator and pints to be in the numerator, because that way the units cancel out to leave us with pints. And then now we find the relationship. Luckily I have this here to be able to at least convert here, but I don't know if it has quartz and pints. We have quartz, but no pints. Unfortunate. So we're actually going to look at what it says here. 1 quart equals 2 pints. So we're actually going to now use what they're saying here in regards to this. It means for every quart, there's 2 pints. So for whatever amount of X quarts, we're going to have twice that of pints. And we can do that because these quarts do cancel out in terms of units, leaving us with the units of pints only, allowing us to now say that the conversion from quarts to pints is that whatever amount there is in quarts, you know, let's say there was like 5.5, that would be 11 pints, okay? And that would be the conversion from quarts to pints. And now let's go on to the next question. For the next question we have, what is a formula for lithium nitride? So this is definitely a great question as well. They're in a sense trying to get you to figure out the name based on what's given. You may already see the answer there, but let's pretend like we didn't, and let's go over to the periodic table. So we're given lithium nitride, okay? Not nitrate, not nitrite, nitride. The ending is very important because it allows us to then figure out what we're dealing with specifically with the nitrogen. So we have lithium, which we can literally just pull straight from the periodic table. It's on the first column, so we just have Li. And because in the first column we assume that it likes to give up one electron. Okay, so we have Li plus as one of the ions. And nitride, okay, the reason why I mentioned nitrate, nitrite, and stuff, because nitride, when you have the IDE ending, it is just the element straight from the periodic table. No oxygens attached, no fancy, I guess, molecule for it. It's just going to be that element. And nitrogen, being on column 15, likes to take 3 electrons, usually, to become an anion of N3 minus. Now, in order for this to balance out, we need the positive and negatives to equal each other. The only way is by having 3 times the amount of lithium to make up for that one nitride, because that nitride has 3 negative. So by doing so, we have Li3N, and that would be the formula for lithium nitride. Okay, let's see how we did. So nitrogen, yep, group 15, column 15, 5 valence electrons. It likes to add 3 more. Lithium, group 1 metal, likes to get rid of its 1. So in order for it to form this bond, lithium likes to donate as many electrons for nitrogen to become complete. So you need 3 lithium to do that. And they actually point out a very important thing here is that lithium nitride, because as you see on the periodic table, lithium is an alkali metal and nitrogen is one of the reactive nonmetals. This is indeed an ionic compound. It's just very important to identify your ionic compounds because they do come in play later on. So this is correct. Let's move on now to the next question. What is the electron geometry of IF4? Of IF4. Whoops. IF4 plus, actually. Wow. That's intense. So that means whatever amount of electrons there are, we literally have to get rid of 4 of them. So iodine, based on the periodic table, I do hope it is 4 plus and not. We'll see, because it might actually be IF4 and then just a positive to get rid of 1. I have not really seen in terms of iodine and fluorine having to get rid of that many, but let's just solve it like the first one just in case. So we have iodine, it's on the 17th column, so that means it wants to have 7 valence electrons for iodine. And fluorine is also on the 17th column, so that means that one is also 7 valence. So in total, we have 14. But if we did the whole IF4 plus, that would actually be 10 because we got rid of 4 electrons. So 10 electrons. And if I put this I and fluorine, right? Assuming this is what it meant. Fluorine is sharing one of its 7, so that's 2, 3, 4, 5, 6, 7. And iodine, same thing, 2, 3, 4, 5, 6, 7. But the issue here is that we need to get rid of 4 electrons. So if I chose 1, 2, 3, 4, this is what we have. And now, if we were then to fix this, because we want us to still complete this octet rule. So in theory, we're going to make these 2 bond with each other, and these two bond with each other. I just do it like that just to make sure that you saw that kind of like the electrons were pairing up. So then now what we have is a triple bond between iodine and fluorine in order to get, let me see, 7, I hope I did the math right. Yes, because 2, 4, 6, 8, 10. Perfect. Exactly. And you should be able to count it and also get 10 electrons, which is what the IF4 plus was hinting at. And to see actually if we had the right amount of charge, we check our formal charges to see if they add up to that ionic charge. I mean, the charge for this ion. So with that being said, I'm just going to do that. Iodine, as we said, 7 valence, so that's 7 minus, it only has 2 by itself and it's sharing 6. So that's 2 plus 3, that's equals 5. So that'll be plus 2 indeed. Same thing with fluorine, 2 plus 6 over 2. That'll be plus 2 as well. So the formal charges, each one does indeed have 2 plus. And that's how we got the electron geometry of IF4 plus. Now if they wanted the other one, IF4 fluorine, so that's going to be iodine tetrafluoride ion, that's a whole different story now, because instead of 7 plus 7, we have 7 plus 7 times 4. So there's 4 fluorines, so we need 7 times 4 at first, then we add another 7. So that's really 7 times 5, but because there is a plus here, it'll be 35 minus 1. So in this case here, we have 34 electrons. Now considering that iodine is by itself, we're going to put that one in the middle, okay? And we're going to now have the 4 fluorines around it. 2, 3, 4. And then circle around IF4. And the fluorines, as we discussed, like to have its 8, well, the rest of it 7, because it's sharing one of its 7, 2, 3, 4, 5, 6, 7. Same here, 2, 3, 4, 5, 6, 7, 2, 3, 4, 5, 6, 7. And iodine is currently sharing 4 of its 7. So it will be 5, 6, 7. And now, you know what, I'm going to draw it in different colors so it's a little bit easier to identify. So I'm going to draw on this side, 5, 6, 7. So there's an extra lone pair right now. But the way to solve that is if there's an extra lone pair and an extra electron. But remember, it's a minus 1 electron because we're dealing with 34 electrons off 35. So just as how we did up there, I'm going to remove this red one right there. So that should be the theoretical Lewis structure. But first, let's check out its formal charge. We're going to start with the fluorines because they're all the same. Okay, it's going to be 7 minus, it has 6 by itself, but it's sharing 2 electrons, so that does equal 0. Perfect. But the iodine, okay, 7 valence electrons, it has only 2 by itself, and it's sharing 8 based on its surroundings. So that's 2 plus 4, that's equals 6. So that's where the plus 1 is. So that does coincide actually with what the charge of this ion is. There's a positive specifically on the iodine. So with that being said, the question is asking for, as you go back to the question, the electron geometry. So because we're able to do now both of these, we're going to quickly solve the electron geometry of both. Now I can say right now that technically speaking, yes, this would just be linear because it's just 2 things attached to each other. So the electron geometry for this will technically just be linear. Typically, the hybridization here would actually just be like sp, and typically we start with like sp2. As you see in the Vesper theory here, as the electron groups, this is based on In fact, this one, yeah, this is, I guess, as quote unquote linear as you can get. It's very interesting. But yeah, so that would be just linear there. But for this, as you notice, if we're going to count how many things it's attached to, which is the electron geometry to find its hybridization, we have, counting first of the bonds, okay, 1, 2, 3, 4 bonds, but we have a 5th thing attached, which is this lone pair. So we have 5 things in total, right? And because of that, we know it's sp3d hybridized, okay? And I can say that because for the S, it has 1 orbital which can fit 2 electrons, okay? P has 3 orbitals which each can fit 2 electrons, and the D orbital has, the D has 5 orbitals which each can fit 2 electrons. So in total, S can only contain 2 electrons. This P3 would contain 6 more electrons, and the D orbital here, just because it's one of them, would have 2 electrons. And in total, it does equal 10 electrons, which coincides with the amount of bond/lone pairs we have, the amount of electrons involved there. So that being said, it's sp3d hybridized, and because of that, it has a specific shape, and that would be trigonal bipyramidal. That would be its electron geometry shape. And if it asks for molecular geometry, I believe it would be seesaw, but it's only asking for electron geometry. As you see here, if I scroll down, 5, trigonal bipyramidal for electron geometry. Its hybridization is definitely sp3d, and exactly as we said, 4 and 1, that would be the seesaw. But that would be the molecular geometry, which is not something we use. Okay, so with that being said, going back to this question, hopefully they got trigonal bipyramidal. So they've drawn it out. They do assume it's the IF4, not the I. They do assume it's iodine tetrafluoride, not iodine monofluoride. And they draw it out there. They add the lone pair, perfect. And because of that, it is a bent shape, but they say, hopefully they have the electron geometry somewhere. Yes, there you go. Trigonal bipyramidal, and they do say that the molecular geometry is seesaw. As long as they have the electron geometry listed there, this is correct. It's just important that you do identify the electron geometry, because you don't want to accidentally call it the wrong thing. Because technically you would be wrong if you said the electron geometry was seesaw, because that would be its molecular geometry. With that being said, let's go on to question 7. Is K2SO3 acidic or basic when dissolved in H2O? So for this one, we kind of really have to, we have no choice but to really separate its constituents and see if we're dealing with any conjugate acids or conjugate bases once it dissolves in water, because we're assuming here that it completely dissociates. So we have K2SO3 dissociating to 2K plus and SO3 2 minus. So 2K plus, we just know that, we know these are going to be potassium ions, okay? Now, for it to be a strong, or if it's, for it to be to work as an acid or a base, it needs to be either able to donate a proton or receive a proton, okay? So it definitely cannot donate a proton because there's no protons available to donate, but can it receive a proton? Potassium has no reason to. It's content the way it is. It wants to stay in this form. So with that being said, potassium is just going to simply stay put. So with this, this would not factor in to whether it's acidic or basic. Let me not make it too extreme. I want you to be able to still read it, but yes, that would not factor in. We're looking at the SO3 2 minus, and that right there is going to be sulfite, I believe. This is a sulfite ion. And this right here can't donate any protons because it has no proton to donate. But if you actually look at your list of acids and bases here, right, you actually see sulfite, hopefully, because that's sulfurous HSO4. But where is, no, it should be HSO3. Big sulfuric is there. Let me just make sure. Sulfuric. There we go. H2SO3. And then we have the next H2SO4. There. So there's just a typo here. This sulfurous should actually be HSO3 minus. And it should be SO3 minus. Because they have the sulfuric here already. As you can see here. HSO4, SO4 minus. So there's a typo here. Just something that we have to just kind of ignore. But the point being is that it shows it as a weak acid. A weak acid means that when you have HSO4 in water, okay, the one that, so this would be the conjugate base right now, and this would be its conjugate, HSO3, sorry. This would be its conjugate acid. It means that when you put HSO3 in water, it does not completely dissociate. It still wants to hold on to hydrogens. So if you flipped it over in reverse, it means that when you put SO3 in water, it would want to take hydrogens from its environment to become that HSO3 minus, which then ties back to what they showed here in this formula here. And when you put the K2SO3, what you're really having is the SO3 minus plus H2O, and that turns into HSO3 minus plus OH, and that'll be SO3 2 minus, sorry, OH minus. And you notice that because the fact that the net charge should still be -2, and you have here 2 minuses on the product's end. All they did here in the formula was just added potassium. But this potassium kind of serves as a spectator ion, because even when it's attached to KOH, like I said, it likes to completely dissociate and stay by itself. You would really just have potassium and then hydroxide ions floating separate from each other, not really attached to each other. So this is really the important reaction happening here, okay? And because of this, if you're able to now take protons from your environment, right, you're working as the base. And because of that, K2SO3 would be basic when dissolved in the water, because it's deprotonating things in the system. It is taking protons from its environment for itself. So that being said, potassium sulfide dissolved in water is going to be basic, okay? And that is honestly just because of the sulfites, not the potassium, because there are such things as neutral salts. So the reason why I say potassium is more of a spectator is because once it dissociates from the sulfur, it wouldn't form KOH. Okay, we wouldn't get potassium hydroxide. It would stay separate. So because of that, saying that KOH is a strong base and KHSO3 is an acid salt, technically correct, but we have to look at it more from this way, where we have it taken from the system, because by saying KOH is a strong base, we're implying that KOH actually takes an active I guess role in making it basic, when in reality potassium is just like, no, I'm fine where I am, I'm not going to interact with any of you people. What's happening here is that by sulfite taking the hydrogen from the water around it, you can see here it's already producing some base, and that's how it works as a base when dissolved in water. So as they actually mentioned here, this is actually a good point they say, is that let's see here, I do believe that they mentioned somewhere that it's a weak acid. Maybe not, it just said that it's an acid salt. But the key thing to remember is that for, I would say, when you look at your acids and bases sheet, or typically when you're dealing with, I guess, specific ions like sulfite, sulfate, dichromate, nitrate, and nitrates, and the one with carbonate. There we go, carbonates, things like that. Typically, when dissolved in water, they do work as bases because they are anions, and they would want to take the hydrogen from the system. There are some few exceptions here. So, like for example, when you have chlorate, for example, okay, chlorate is such a, I guess, independent anion that completely dissociates from hydrogen. So theoretically, if I were to add NaClO4 into water, this would be a theoretically neutral, because there's no reason where ClO4 plus H2O would go into CHClO4, because they don't want to be together at all. So theoretically, this would be a neutral compound. But that's just in theory, though. The point being is that you want to look at the things that, aren't strong acids. Specifically, you want to look at, there we go, the conjugate acid of your anion. Typically, you want to make sure that it's not a strong acid, because then there's hope for it to be able to now form its conjugate acid when put in water. When the conjugate acid is a strong acid, like for example, if you have HCl, if you added like literally salt, which we all know, NaCl, that's a neutral compound, because HCl, its conjugate acid, is a strong acid. NaOH, for example, that would be its sodium's conjugate base or something. That one is a strong base. So that's why these two things, when added in water, you will see that there's no shift in the pH, because both of them don't want to be with OH or the H. They want to stay by themselves. So yeah. Nonetheless, though, this is correct. It's just that I do just want to emphasize that your pH changes typically comes from having a weak conjugate other, and not a strong one, because a strong one means that it wouldn't want to get back together. Question number 8. Name these alkenes. Okay, so here we're doing a bit of nomenclature. Pretty sure I butchered that word, but no worries. We're here to name these compounds, not rate my pronunciation. With that being said, we have we have, if I counted correctly, hopefully, and these are alkanes, so they do follow the CNH. So I'm going to write it here. They do follow the CnH2n plus 2 rule, because they say alkane, ANE, and that means it's completely saturated. That's why we can follow that rule. So what I'm going to do here to save you some time, I'm just going to count the carbons, okay? And based on that, I'll be able to hopefully name the alkane, okay? So we have right now 5. 1, 2, 3, 4, 5 for A. So it kind of goes like, okay? Now that I've drawn that, we have 1, 2, 3, 4, 5 carbons. So really, all this one would be if we had our handy sheet, well, not sheet, like memorization, memorized. We have pent. So there is propane. That's 3. So it's prop is 3. Bute is 4. Meth is 1. Don't know why I was blanking out. 4. Bute is 2. Where is it? Pent is 5. Hex is 6. Hept is 7. Oct is 8. Non is 9. And dec is 10. So because there's 5, and we know that it just follows the CnH2n plus 2, that's how we get the ending of the A and E for the alkane. We have here pentane for the first one. Now for B, we have 1, 2, 3, 4, 5. Okay, so we have kind of like this again. Sorry, let me draw that better. All right, and in the middle one, we have 2 bonds sticking out, and we have one up here, and the ending here, we have something that looks like this, okay? So in total, hopefully when we circle them, we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. 3, 4, 5, 6, 7, 8, 9, 10. Perfect. But we wouldn't just say this is decane. Because there are actually branches here, we have to make sure we account for them. So what I'm going to do here is try to find the longest branch based on what's given. And I can see it that if I start from this end, I can go 1, 2, 3, 4, 5, 6. And you would notice that there's no other way for me to go to where there I would get a longer branch. Now, the reason why I chose this order specifically is because I also want my 1 to kind of start where most of the action is taking place. So as you can see here, the 5 has a bond. I mean, it has something sticking out, yes, but 1 through 3 is really where all the action is, where you have the most chains coming out of it, okay? So because our longest chain is 6, it's going to end in hexane, okay? And now, we count how many of our different, I guess, chains we have. We have 1, which is meth here, okay? But there's 2 of them at 2 and 5. So we have 2, 5, meth, okay? Methyl. That's how we would call it. You get to add the YL instead because it's part of the bigger chain. And then we have 3, and there's 2 of them here, so that we have 3 ethyl, okay? So with that being said, because the actual rule, surprisingly enough, is that we want to actually go alphabetically. So even though technically methyl is a shorter chain length, ethyl E comes before M, so we actually have 3 ethyl. Whoops, sorry. 2, 5, and it'll actually be not just methyl, but because there's 2 of them, you have to indicate that. So there is quite a bit of things involved. Sorry, I thought I put F here. There we go, meth F. Don't know how I got. Yeah, okay. And I don't know why I put butyl here, because it should be but. There we go. Sorry about that. So we have 3 ethyl, 2, 5, and now here's, funny enough, another name that we have to remember. We have mono, which is never really used in this case, but we have 2, 5. We have di, we have tri, and we have tetra. We don't really go further than that typically, but we have here, we use 2, 5, dimethyl. And that would be how you would name this specific. And let me just write it here, because mono is 1, di is 2, tri is 3, and tetra is 4. Okay? And that would be our name for this alkane. And now for the last one, we have C. This is a big one for sure. And we're gonna have 1, 2, 3, 4, 5, 6, 7, 8. Just wanted to count my longest chain, so it'll look kind of like this. Oops, that's too many. 4, 5, 6, 7. There we go. And it looks like on the 4th one, there's stuff sticking out, where it goes like this, and it kind of goes like that. Oops. Okay, and on the bottom we have something like this. Okay, well, technically more like that if you wanted to be accurate to what the picture is saying over there. But we still should get the same name. Now, the one thing I'm going to address right now is this thing, because this thing, the naming for it is not so simple. Okay, we're going to leave that for now, but I'm going to stress right now, when you see something like this is what we call iso. Okay, but we will film the rest of it later. Just wanted to point that out. So now the same thing here, we want to make sure we go by where most of the action is. So right now we have our 8, 9, 10, 11, 12, 13, okay? So we have 13 there, and we want to see if we have the same amount. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there we go, 13 for both. We're good to go. And let's see where the most action is. Well, it's almost like an even split, but as you can see, there's 3 carbons on one side, kind of like we split it right here. There's 3 on this side on the left and 2 on the right. So with that being said, we would want to start from the left. So we have 1, 2, 3, 4, 5, 6, 7, 8. So right now we know that our ending is going to be octane. All right. And now we're going to finally address the elephant in the room, which is that iso part. So because it's still 3 carbons, that would still be propane. But typically, if propane was going to stick out, it looks something like this. Okay? It looks something like 1, 2, 3. And I drew it like that because I want to easily erase. Because what's happening is that 1 carbon, instead of it being just sticking out like that, we have it now where it sticks out of the carbon in the middle. And that's how it gets its iso name. So in full, really, this would just be isopropyl. Because still keep it with the YL ending, but you just have to make sure you add the iso with it. And now because you added the iso, it it will change in the order based on the alphabetic. Okay? And luckily enough, though, we do have ethyl, so it'll come before it anyways. And now we just say where it occurs. So we have 5-ethyl, 4-isopropyl. 4-isopropyl. Oops, spelled that wrong. Isopropyl octane. So 5-ethyl, 4-isopropyl octane. And now we've labeled all 3. We have pentane, we have dimethylhexane, and we have pentane, 3-ethyl, 2,5-dimethylhexane, and 5-ethyl, 4-isopropyl octane. Let's see how we did. So this one, pentane, yep, 3-ethyl, 2,5-dimethylhexane, and 4-ethyl, 5-isopropyl octane. Perfect. So this is correct. But interesting, they have 4-ethyl, 5-isopropyl. They say because ethyl is high in alphabetical order, you assign the 4 to it. But what I've learned, at least from my perspective, is that you want to assign the, I guess, you want to put the end where it starts and where, like, hopefully you get to the most chains, as in the most carbons. So because ethyl, even though it's alphabetically more in front, because it has less carbons than isopropyl, that's why I chose 4 there. You would even notice that even the IPAC ruling, there are some, I guess, little hiccups to it, because it's a lot of, and there's like a lot of infinite combination of what molecules could be brought together and to name, even for alkanes, which is why it's just important to be able to at least explain and reason and keep consistent with how you're naming it, because that way you don't confuse yourself of what molecule you're talking about. So now question number 9, okay? We have here, what is a molar mass of magnesium? Oh, sorry, I can't do that, because that's part of finding it out. Magnesium, oh, you see the answer there anyways. But let's pretend like we did not get the answer right away. So we got magnesium and nitrate, molar mass. Magnesium, we can just say it. Periodic table, we look at it, we see it's Mg, and because it's on the second column, it's an alkaline earth metal. It typically likes to get rid of 2 electrons. So that's Mg 2+. So we figured out magnesium. Nitrate, on the other hand, unfortunately something I have to memorize, because it wouldn't just be a nitrogen, okay? it'd be a nitrogen with 3 oxygens. That is nitrate. And nitrate specifically has a charge. It's an anion. It has just one negative charge. So this is nitrate, and that is magnesium. And because magnesium is a metal and a nitrate anion is a non-metal, this is indeed an ionic compound. Just to be able to get that out of the way. You won't need it for this question. It's just important to be able to identify them. With that being said though, we want a net charge of 0. And right now, if we did 1:1 ratio of magnesium to nitrogen, we still have a positive charge of 1 still. So we need 2 of the nonmetals, the nitrates, to be able to make up for the Mg, the magnesium. Okay, so we have Mg, NO3, 2. That would be magnesium nitrate. With that being said, let's add the constituents. We only have 1 magnesium, and then based on this, if we multiply the 2 by each one of them, we have 2 nitrogens, okay, and we have 6 oxygen. So magnesium, based on the periodic table, is 24.305. Nitrogen is 14.007. So that's good. And oxygen is right next to it, 15.999. So if we now were to add everything up, first we multiply. So that's 14.007 times 2, that's 28.014. And 15.999 times 6, we have 95.994. So we're going to add everything up together, because what I've done is I've gotten the atomic mass units of its constituents and add them all together to be able to get its molar mass. And once I put that in the calculator, we should be able to find our answer, plus 28.014. In total, we get 148.313 grams per mole. That right here is a molar mass of magnesium nitrate. And that is actually really close to what they got. But as you can see, their numbers slightly vary based on the periodic tables they used. The point being is that we did get the same molecular structure for magnesium nitrate. That is a chemical formula indeed. And based on that, they got the constituents and they were able to get the molar mass. So now let's move on to question number 10. So we have density of gold is 19.3 grams per mil. Okay, what volume let's see, well, I mean, you may already see the answer there, but what volume will 1.592 pounds sample gold occupy? Okay, so with that being said, we first need to get that pounds into grams, and then we can work in the density. Okay, because right now trying to convert from the pounds using density, it wouldn't make much sense because the units don't cancel each other out. So we start out with 1.592 pounds, and first we need to find out how many grams are in 1 pound. Hopefully I have a unit conversion for that. Let's check out our table. So for this, it's loading up. For units of volume, units of mass, there we go. 1 gram is 1. Oh wow, that's a lot of. Oh, that's a lot of gold. So we have here that 1 kilogram is 1,000 grams, which is 2.205 pounds. So actually what I'm going to do here is convert first to pounds to kilograms. So we have 2.205 pounds is equal to 1 kilogram. And then we have 1 kilogram is equal to 1,000 grams. Okay, so now we've gone into the grams part. So the next thing we have to do is, sorry, I don't know why this thing is, there we go, is go from grams to mils using the density. Density says 19.3 grams per mil. So that means per 1 mil, there's 19.3 grams. Okay, so now if we check through, all our units should cancel out to where we're just left with mil, which is correct. So we're going to multiply all our numerators, which is going to be 1.592 times 1,000, divided by all our denominators, which is 2.205 and 19.3. Because 1.592 times 1,000 divided by 2.205 divided also by 19.3. Okay, and in total what we get is 37.41. I'm going to keep it there because I want to use 4 significant digits, considering we started the sample goal was 4 significant digits. So with that being said, we have 37.41 mils. So hopefully we did this correctly. Let's see here how we did. As I said, they got 37.42, so maybe there was a little bit of rounding on their part because I don't remember rounding on my part. It depends on how they converted the mass in terms of the pounds. So we have here 1.592 pounds, and they say there's around 453.6 grams per 1 pound. So they did like a direct conversion. Even if I did that, 1,000 divided by 2.205, I get there's around 453.5 grams per 1 pound. But the change is so minuscule, considering that we almost got literally the same answer still. But yes, they converted from the pounds to the grams, and then they went on to convert the grams to a volume based on the density distribution, the grams per mil. So that is correct for question 10. With that being said, just going to take a quick little water break. Or smoothie. We're going to move on now to the next question. First, want to see how we're doing with the stream. Oh, interesting. I'll be right back. Wow. Hello there. Sorry, but it looks like we're experiencing some technical difficulties, so we will have to end the stream here for tonight. You have a lovely rest of your evening. Happy New Year's once again. And yeah, definitely check out the links in the description below if you have any further questions. Thank you.